In this video, I will teach you how to approximate the value of a function at a point using Euler's method. This is a BC-only topic. A long time ago, we learned how to estimate the value of a function using a tangent line approximation. Let's review that process briefly, because Euler's method is an extension of this process. To find the equation of a tangent line, we always use point-slope form because all we need is a point and the slope. We are told that the point of tangency is at x equals 1, so we know the x-coordinate of the point is 1. We just need to find the y-coordinate, which will be given by this equation. So y will equal the natural log of 1, and the natural log of 1 is 0. So we've got our point. Next, we need the slope of this curve at this point. But in calculus, we know that the slope of a curve at a point is the derivative. And in this case, y prime is 1 over x. X is 1, so y prime at x equals 1 is 1 over 1, which equals 1. So the slope is 1. Now we can write the equation of the tangent line, which is y minus y equals the slope times x minus x, which simplifies to y equals x minus 1. Now let's use this tangent line to approximate the natural log of 2. The natural log of 2 is approximately equal to 2 minus 1, which equals 1. Let's use calculus and concavity to determine whether your approximation for natural log 2 was an overestimate or an underestimate of the true value. Justify your answer. Our analysis will be based on the second derivative, but first y prime is equal to 1 over x, which can be written as x to the negative 1 power. So now we can see that the second derivative, y double prime, is negative x to the negative 2 power. Y double prime can be written as negative 1 over x squared. Notice that this expression will always be negative. X squared is always positive, and then the negative 1 makes it negative. So y double prime is always less than 0. We have learned that wherever the second derivative is negative, the original function is concave down. We also know that natural log looks like this, but we needed this analysis for our justification. If a function is concave down on a particular interval, a tangent line approximation will always give an overestimate because the tangent line will always be above the curve. Here's the justification. Natural log 2 is approximately equal to 1 is an overestimate because y equals natural log x is always concave down, so the tangent line is always above the curve. Confirming with the calculator, notice that natural log 2 is actually 0.693. We can get a better approximation using a process called Euler's method. Notice that this is pronounced Euler's method, not Euler's method. Here's an illustration of the tangent line approximation we just did. Notice it gives us an estimate which is here, when the true value is here. The big idea behind Euler's method is that we can improve our approximation by using multiple tangent segments instead of a single tangent line. For example, we can use the original tangent line for this first step from 1 to 1.5. But then if we can somehow recalculate the slope at 1.5, that will give us a new tangent line from 1.5 to 2.0. Notice that our new estimate is significantly closer to the actual value than our original estimate, which used only one tangent line. You can imagine that our estimate will get better and better if we use additional segments. Here's the information we need in order to use Euler's method. We need the initial condition, which is a starting point. We need the step size, which is the horizontal width of each segment. and we need the number of steps, or the number of segments. For Euler's method, we make a table that shows the endpoints of each segment. I want you to memorize this setup. You need to memorize what goes in each column. To find the endpoints of all the segments, you need delta x and delta y. You are always given delta x because delta x is the step size. The question is, how do we find delta y? We know that y prime is equal to dy dx. When we do an approximation like this, we can say that y prime is approximately equal to delta y over delta x. This is the slope of a segment as opposed to the slope of a curve at a point. Remember, we are trying to find delta y, which is right here in the numerator. To get delta y by itself, we could multiply both sides by delta x. That would give us delta y is equal to y prime times delta x. So that's what's going on here. For this problem, we are given the initial condition that the natural log of 1 is 0, which translates into the point 1, 0. These first two columns are for x and y. So x is 1 and y is 0. As I mentioned, we are also given delta x, which is the step size of 0.25. Given the initial x value and the step size of 0.25, we can find all the x values. We just have to add 0.25 each time. So the next x value will be 1.25. After that, we get 1.5, 1.75, and 2. To get the next y value, we need to know what delta y is, the change in y. But to find delta y, we first need y prime. Remember, the original function is y equals natural log x. So, y prime is 1 over x. I'm switching to light blue now because these next two boxes are meant to help us calculate this next y value. So first we need y prime at x equals 1. So since y prime is 1 over x, that is 1 over 1, which is 1. Now delta y is approximately equal to y prime times delta x. So that's going to be the 1 that we just found times the delta x of 0.25. So that gives us 0.25. So we just found delta y. That's the change in y. So to get the next y value, we take the previous y value and we add delta y. 0 plus 0.25 is 0.25. Then we just repeat that process over and over again. So next we need y prime at 1.25. So that's 1 over 1.25. Let's use a calculator. That's 0.8. Then delta y is y prime times 0.25. Back to the calculator. There's my y prime, so I'm just going to hit times 0.25. And that's 0.2. To get the next y value, we need to take the previous y value plus delta y. So we need 0.25 plus 0.2. 0.2 is already in the calculator, so I'm just going to go plus 0.25. So this is the next y value. Let's do it again. Y prime at 1.5 is 1 over 1.5. That's 0.667-ish. Alright, I'm going to keep all of those decimals on the next step. So for delta y, we need to take our y prime, our 0.66 repeating, and multiply it by the delta x of 0.25. So remember, we already have the y prime in the calculator. So we just need to multiply by 0.25. So that's 0.167 about. This is delta y. To get the next y, we need to add delta y to the previous y. Since delta y is already in the calculator, I'm just going to add the previous y, 0.45. So this is the new y. In my work, I'm going to write 0.617, but I don't want to lose any of these decimals, and I am going to need this value later. So I'm going to store this in a letter on my calculator. So let's hit store, and let's just put it in letter y. Let's do one more iteration. We need y prime at 1.75. So that's going to be 1 over 1.75. (0.571). Now we need delta y, so we need to multiply y prime times delta x. Y prime is already in the calculator and I don't want to lose any decimals, so I just need to multiply by 0.25. And we get 0.143. This next y value is going to be the final answer. We need to take delta y and add it to the previous y value. Delta y is already in the calculator, so I just need to take what's in the calculator and add the previous y value. I don't want to lose any decimals, so I'm going to use the value that I stored into letter y. So in my calculator, I'm going to take what's already there, and I'm just going to do plus letter y. And this is the final answer, 0.759 if you truncate, or 0.760 if you round. So this is the final answer. Here is the graph of y equals natural log x. Let's plot these 5 points on the graph so we can see the segments that we are using for this approximation. At an x value of 2, the actual value of natural log is here, and our approximation landed here, so it's very close. A colony of bacteria grows according to the model dp dt equals p times 5 minus t, where p is the population of the colony and t is the number of hours that have passed since noon. At 4 p.m., there are 100 cells in the colony. Predict the population at 4:45 p.m. using Euler's method with 15-minute intervals. Round your final answer to the nearest whole number. This statement gives us the initial point 4, 100. For this problem, we are using t and p instead of x and y. So instead of delta x, we will talk about delta t. Delta t is given by this statement, but be careful, delta t is not 15. Time is being measured in hours. 15 minutes is a quarter of an hour, so delta t is 0.25. We are given the derivative right here, so p prime is equal to p times 5 minus t. We are being asked to predict the population at 4:45 p.m. This is 4 3/4 of an hour. In other words, t equals 4.75. So we are being asked to take these 3 pieces of information and figure out what the population will be at t equals 4.75. The top row holds the setup, so this is the part that you have to memorize. The first 2 columns are for x and y, or in this case, t and p. In the next column goes y prime. In this case, it'll be p prime, which equals p times 5 minus t. In the last column, this is where we calculate delta y, and we get this by doing p prime from the previous column times delta t. Memorize this. The initial point goes in the first two spaces of the second row. We can get the rest of the t's by adding delta t repeatedly. For example, the next t is going to be 4.25. The next two t's will be 4.5 and 4.75, and the final answer will show up right here. Let's pick up right here on the table. We need to find p prime at 4, 100. So p prime is equal to p, 100, times 5 minus t, so 5 minus 4. 5 minus 4 is 1. 1 times 100 is 100. Delta y is p prime times delta t. P prime is 100, so we are going to multiply 100 times delta t, which is 0.25. And that is 25. We need to take this delta t and add it to the first p. That will give us the next p. So 100 plus 25 is 125. So this is the next p. Now let's do it again. P prime is p times 5 minus t. So that's 125 times 5 minus 4.25. That's 93.75. Next, delta y is p prime times delta t. That's 93.75 times 0.25. 93.75 is already in the calculator, so I can just go times 0.25. 23.4375. To get the next p-value, we need to take the delta y and add it to the previous p-value. So I need to take the number in the calculator plus 125. So I just hit plus 125. 148.4375. Let's do one more iteration. P prime is p times 5 minus t. So it's going to be this number times 5 minus 4.5. This number is already in the calculator. So I'm just going to do times 5 minus 4.5. Obviously this is just 0.5, so I could have just done that. Anyway, we get 74.21875. Next we find delta y by doing p prime times delta t. That's this number times 0.25. This number is already in the calculator, so I'm just going to hit times 0.25. Kabam! And finally, we get the last p-value by adding delta y to the previous p-value. Delta y is already in the calculator, so I'm just going to add 148.4375. Kabam! This is the final answer, but since this was a real-world problem, let's write the answer in the form of a sentence. Remember they said to round to the nearest whole number, so at 4:45 p.m. there are about 167 bacteria. I just realized I made a small mistake right here that does not affect the final answer. I've been saying delta y this whole time, but we are using p instead of y, so I should be saying delta p. That's better. And here's a graph of the Euler's method approximation featuring the 4 points we just found. Here's the initial point and the final answer.